Another gravitation example here. What I have here is a satellite orbiting 200 kilometers above the surface of the Earth. So here we have the Earth with a radius that we call r subscript e, which we know to be 6.38 times 10 to the 6th meters. We look at that. We also have the distance from the Earth to the satellite, which is 200,000 meters, or 200 kilometers. We also have the mass of the Earth, which is 5.98 times 10 to the 24th kilograms. We don't know the mass of the satellite. We'll see if that even makes a difference later or not. And of course, we know the Earth's gravitational constant is still 6.67 times 10 to the negative 11th. So I first asked you to determine the speed of the satellite. So as we look at this problem, first things first, we want to look at our good friend, the force of gravity equation that says Fg is equal to Gm1 m2 over r squared. And it's important to remember that whenever we're talking r, that's the center to center radius. So as we're looking at things here, we are taking a look at from the center of the Earth to the center of the satellite. So when we go through and calculate r, we actually need to add the radius of the Earth right here to the height above the satellite above the Earth. So we take the 200,000 meters plus the radius of the Earth, 6.38 times 10 to the 6th meters, and we get 6.58 times 10 to the 6th meters. So that's important to know that we're talking center to center when we're talking that r in our equation. So, as we look, I want to find the speed of the satellite. So, we need to find the velocity of that satellite right here. So, looking at this, we want to require and look at some old centripetal acceleration problems, because it's actually gravity that's causing the centripetal force. So, we'll write it as Fg is equal to Fc. So, if we write our equation, force of gravity, G, m, and as we're looking at that, that's the mass of the Earth times the mass of the satellite over r squared is going to be equal to the centripetal force, which hopefully you remember is mv squared over r. So as we're looking at this particular equation, when we look at mass, I'm asking you to find the speed of the satellite. So we're going to look at the mass of the satellite, so I'll call that m subscript s. So we do a little algebraic manipulation here and solve for v squared, and we're left with v squared is equal to g, mass of the Earth, times mass of the satellite, times r, over r squared times the mass of the satellite. So as we see here, bing bing, mass of the satellite cancels out. The radius on top cancels with the r squared at the bottom here. So we're left with v squared is equal to g times the mass of the Earth over the radius. We want to get rid of that squared, so boop, we take the square root of both sides, and we get velocity is equal to the gravitational constant times the mass of the Earth over r. So this is a general formula. You're going to see a whole lot that says the orbital velocity is equal to the gravitational constant times the mass of the object that's being orbited, in this case that's the Earth, divided by the radius. So as we go through here, we're going to see that we end up having, if we plug in g 6.67 times 10 to the negative 11th, the mass of the Earth, and the radius, we get a velocity equal to 7,786 meters per second. So there's part one. We found the speed of the satellite. Yay, that's a good thing. I'm going to go to another page and now find the period of the orbit. So let's add another page. So if we look at a little review here, we remember the period, and we're on part B. Period is abbreviated by a capital T, and that's the time to complete one revolution. So that's that satellite going all the way around the Earth one time. And then we remember the term frequency. That's just a lowercase f. And that's the number of revolutions per unit time. And that'll be helpful here momentarily. So as we look at this, let's just look at a basic circle here. Let's pretend that that's our Earth, and we have, woohoo, a satellite orbiting that. We would have a radius r, and hopefully that would be drawn a little bit better, but it's not. We'll deal with that. We look at that, and the distance that that satellite is traveling in one full period, one full revolution, that distance is going to be equal to 2 pi r, simply just the circumference of our circle. So we look at this, we know our velocity is equal to 7,786 meters per second. That's what we saw for earlier. And we want to know the time it takes to go a full 2 pi r, one full rotation around the Earth. So we remember a good old friend, velocity is equal to the distance divided by the time. So that's going to mean that's equal to 2 pi r over t, and t would be the time for one full period. So we can say the time is equal to one full period, which we do a little algebraic manipulation and solve for t. We end up with 2 pi r over the velocity. So we go through and find the period, capital T, and we simply just plug in values that we know, and we get the time is equal to 5,310 seconds, which is about 1.5 hours. So there you go. Now, as we look at this again,